So today, well, yesterday, we spent a lot of time talking about CO2 systems. I would title this session also Alternatives to CO2 Transcritical. Today, we're going to talk about distributed and self-contained systems, where our goal here is to hear from retailers and their partners to share experiences about these system types with alternative refrigerants, including propane and other options. So our presenters today, Michael Dellecave, Manager of Mechanical Systems with the Kroger Company, Andrew Beall, Director of Refrigeration and Energy with WinCo Foods, and Ben Rosenzweig, Vice President and General Manager of CoolSys Energy Design. So first, I'm going to hand things over to Ben to give us an overview of the system types that we'll be talking about today.
Hi, good morning, everyone. I'm Ben Rosenzweig. I manage CoolSys Energy Design, consulting engineering firm specializing in MEP and refrigeration systems. And I'm looking forward to framing the conversation today, providing some background on distributed and self-contained systems as they relate to all of our goals of reducing greenhouse gas emissions and implementing lower and no GWP refrigerants into supermarket and other forms of retail. I do acknowledge that the distributed system refrigeration architecture is one that's been around for quite some time, but there have been many advancements even in the past year or two, and it's always worth making sure that all the retailers and end users across the country that have yet to adopt something like this know what's going on. So today we'll define some of the key terms, talk about pros and cons, and do a bit of a deeper dive on micro-distributed systems, which are becoming more and more popular in the use of low GWP refrigerants. Next slide. So just really quickly to go over kind of the three main system architecture types we'll talk about today in different levels of detail. The first is what I'll call a traditional distributed system, but for the purposes of this conversation, we'll call a macro distributed system. And this type of system is one where you might have several small to medium sized compressor racks with multiple compressors, kind of looking like a traditional central refrigeration rack throughout a retail store located strategically near case and coil loads. These are typically popular to reduce refrigerant charge, potentially increase energy efficiency and compressor selections, as well as reduce piping in the store, etc. These can be used with low GWP refrigerants, including CO2, depending on the size of the systems, and typically have remote condensers or gas coolers for each individual system that might be located on the roof or somewhere else outside the building. Self-contained systems, to me, is kind of a general term covering packaged refrigeration equipment and fixtures that typically don't require remote equipment to operate, other than for, say, electrical connection and sometimes a plumbing drain. Even, for instance, a product merchandising fridge at a check stand would qualify as a self-contained system, and frequently those only need to be plugged in to an electrical receptacle. But self-contained systems and self-contained equipment are an important component of micro-distributed systems, and we'll talk a lot more about those today. Micro-distributed systems are different from macro-distributed systems in that there are many, many small compressor systems distributed throughout a store, typically located along case lineups, behind them, beneath them, on top of them, and in place of traditional walk-in refrigerator and freezer evaporator coils as packaged equipment. In many cases and applications, these are comprised of interconnected or independent self-contained equipment components, and we'll talk a little bit more about that. Next slide, please. So to quickly go over macro distributed systems and their difference between central traditional systems and distributed refrigeration architecture. On the left side of the slide, you kind of see a very simple diagram of a refrigeration cycle in a retail store where you might have a mechanical room or other equipment area where your compressor rack and receiver is located. You might have a condenser on the roof above that. And then you have piping throughout the store, through the sales area, above the ceiling, to all the different loads and coils in the store, but it's all going back to one central location. Lots of piping, large refrigerant volume and charge in the store. And if you listened yesterday, you know there are ways to implement low GWP refrigerants into those types of systems. but today we're going to talk about some alternatives to that. So in a macro distributed refrigeration system, you'll have, like explained, multiple smaller systems that look like central refrigeration systems. However, the mechanical equipment, the compressor equipment, the receiver, that kind of rack package is located much closer to the individual loads that rack might be serving. The designer who puts that together can then more closely specify and design the specifics of that compressor system for the loads, the suction temperatures required, and the cases and coils that it's serving, thus reducing refrigerant charge, making other refrigerants potentially an option, as well as different design styles. This has been a popular system architecture that many retailers have used for decades in the United States and continues to be with low GWP refrigerants. Next slide, please. So some of the quick pros and cons about macro distributed systems are there's air and water cooled options. They're very flexible. Lower than 50-pound charge systems qualify as low charge systems in many places. You can use CO2, and they have similar controls to traditional central refrigeration systems, which could be easy in terms of installation and maintenance on that side. Some of the challenges or downsides might be that equipment installation can be complicated depending on the building architecture and structure. The high side piping system almost is always required in terms of meaning you have a remote condenser that you have to pipe the refrigerant to, which could lead to a larger refrigerant volume, more distributed items to maintain, and it's not necessarily energy saving over a central system depending on the design. Next slide, please. Now we'll talk about micro distributed systems, and we'll focus a little bit more on this for the rest of the conversation. And this here simply is a very simple diagram of what a micro distributed system might look like from a flow perspective, where you have, say, 3 refrigerated cases next to each other that are each served by individual compressor systems that sometimes have just one compressor in them, serving one evaporator, using capillary tubes for refrigerant flow control or other control methods. And these can be air and water cooled. So where you see the water cooled condenser on the top there, that could be replaced by individual air cooled condensers, or you could have a central hydronic water glycol loop through your store that you're using to reject the heat from these systems and take it outside to a dry cooler or other piece of equipment. Next slide, please. So this here shows you kind of a view of a potential retail store in 3 dimensions, where you can see that you can have multiple case lineups and coils for walk-ins that are in parallel and in series. And you can kind of apply this micro distributed and self-contained architecture to the entire store, where you might have specialty merchandisers or island cases or custom cases. You can implement those with low GWP refrigerant options like propane and some others that we'll talk about, as well as connect the case lineups and coil units to, per se, a central water loop for energy efficiency purposes, up to some kind of dry cooler or fluid cooler on the roof. Again, you can leverage natural and synthetic refrigerant options throughout the store. This is highly flexible, and there's many different ways to look at it. Next slide, please. So some of the pros and cons about micro distributed systems are different than those of traditional distributed systems. While many of the pros are similar, but played even further upon, there are air and water cooled options, and you can use both in the same store for flexibility. These cases and coils are not piped to central racks, so you have physical flexibility in relocating and adding new cases to your store. All system charges in micro distributed systems are lower than 50 pounds. There are many natural refrigerant options. Typically now, R290 or propane is one of the most popular. However, I will talk at the end here about a CO2 application with a micro distributed system, which is really, really interesting and may be widely popular in the future. Most water cool units for R290 and other systems have a very wide inlet water temperature range, so you don't need a chiller in order to run those. And there's much less complicated control systems. Many of these pieces of equipment and cases are controlled similarly to a refrigerator at your house, where you kind of plug it in and select the temperature and let it do its thing. Some of the challenges are, and really the primary challenge is, that right now, the most popular and widely available refrigerant for self-contained micro-distributed systems with a low GWP is propane. And based on the construction codes and other regulations, there is a limit of 150 grams per charge with these systems. Therefore, you need many, many compressor systems throughout the store in order to comply with that. You know, when that charge limit is increased, the flexibility will be enhanced and there'll be more options, less compressor systems, etc. If you go with air-cooled equipment, it does reject significant heat into the store, which can be used, but also can cause a significant load on your HVAC system. And if you implement something like this without looking at that, you could have a problem. There's many distributed items to maintain. Again, it's not necessarily energy savings, but you can design it with parity to central systems. And there are fewer controls options here. Next slide, please. So what refrigerants are being used? Propane, as I mentioned, is the most popular low GWP natural refrigerant choice for micro-distributed systems. R448, which is a very popular synthetic, but with a high GWP, is popular amongst less than 50-pound qualifying system architectures. A1 and A2L refrigerants are being tested throughout the different types of equipment ranges, and more will become available. And CO2 is a popular option for macro-distributed systems and soon will be for micro-distributed systems. Next slide, please. So the most widely used commercially available options here, and not all are listed, are things like the Hussmann Micro DS and Micro SC options, which are air and water cooled propane, the Hill Phoenix Solo Chill and Second Nature options, which are DX as well as self-contained using either R448 or propane, AHT cooling systems, air and water cooled units that use R290. Emerson's Copeland Indoor Modular Solution, which uses R448 and R290, and Novum Leap self-contained equipment using R290. Next slide, please. So just briefly, while I wrap up here, look into the future is something like this, where you can have a system based on subcritical CO2 as the refrigerant cycle, where it's a truly micro-distributed system using a water loop, where you're using CO2 with the reference GWP of 1 as your refrigerant, even lower than propane or some other options. And you'd be able to place these units throughout the store. You'd have a water loop, albeit it would need to be using a chiller to get the temperature low enough. And that chiller should be specified with low GWP as a refrigerant in order to continue down the path of designing low GWP stores and not increasing the amount of GWP that your store might have. So these have CO2 condensing units distributed throughout the store. The chilled water loop can be used with the air conditioning system and other options to create a really fully integrated HVAC and refrigeration design. And there wouldn't be any kind of charge limit at all because it's CO2, which means more fixture options and flexibility for the future. And one of the options that's currently being marketed and presented around this is the Carrel Heliospox CO2 system, which was demonstrated a little earlier this year at Chillventa. So next slide, please. So this is my last slide, and then I'll wrap up. Application in existing stores. So you have the option to install a store-wide water loop with capacity for progressive remodels and low GWP conversion at existing stores, replacement of traditional case lineups and walk-in systems with low GWP alternatives, one by one, whole store, department by department, depending on how you want to do it. There are now many commercially available like-for-like island and specialty merchandiser cases that are now available. And you should carefully consider the impact of air-cooled equipment on existing store HVAC systems. So really, when you implement this type of system into an existing store, it's important to work with your designers and your engineers to make sure you're getting a system that won't sacrifice the environment in the store from an HVAC perspective, but can help you achieve your low GWP goals as a company on a store-by-store basis and across the country. I think that was my last.
Yes, thank you so much, Ben, for that overview. That was really helpful. I do want to address one quick question that came in because it's relevant to our discussion today around the increased charge size for propane that you mentioned. So you showed that, you know, the current charge limit according to many building codes and standards in many states is still at 150. However, the UL standard was updated in 2021, actually, to allow for the higher charge limit. That is now making its way through the various other codes and standards that need to be updated. So ASHRAE 15 was updated. There's a EPA SNAP application in that's expected to go through by, I think, mid-year next year. And then the real work is in updating each individual state's building codes in order to allow for that higher charge limit. So that work is being done now. I will call out AHRI has a great kind of partnership that they've developed. A number of organizations participate in, including NASRC, and they are really spearheading the effort to increase the charge limit for A3s, which is propane, as well as A2Ls that we'll talk about here in a minute. So thank you so much, Ben, for that overview. And next, we're going to hear from Michael Dellecave about some perspective from Kroger and experiences that Kroger's had with distributed systems.
Thank you, Danielle. So my name is Mike Dellecave. I'm our manager of mechanical services. So my department handles our refrigeration design and applications in all our stores. We operate over 2,700 stores in 35 states. And I kind of just pointed out in the fact that while we're evaluating new systems, we operate in almost every climate zone in the country. So we have to pay attention to elevations, to cold climates, warm climates, dry climates, wet climates. And with these future technologies, sometimes that does pose interesting challenges. So go ahead and jump into the next slide. From our sustainability report, Kroger's current target is to reduce our greenhouse gas emissions by 30% by 2030. Obviously, refrigerants play a very important role in achieving that goal. And we kind of take a four-pronged approach to what we do with our refrigerants. Proactive leak monitoring, mitigation, and reduction. That's really step one. Replacing our aging refrigeration systems. This obviously will bring in a lower GWP refrigerants often and obviously improve our energy efficiency. Proper management of refrigerant inventory that reduces our waste and obviously ensure responsible reclaim practices. And then our transitioning to refrigerants with lower global warming potential. Won't point out though, low GWP is part of the equation. A lot of the other work, reducing our charge, limiting leaks, and keeping efficient systems, installing efficient systems are essential to lowering not only your direct greenhouse gases, but your indirect greenhouse gases. So just because you have a low GWP system, and if it's not running efficiently, you might not be lowering your GHGs as much as you anticipate. Next slide, please. So our current system architecture, which is kind of been what we've done for the last several years, is a distributed design. Typically in our stores, which are our current standard store is 120,000 square foot. We have 4 or 5 distributed units that are utilizing an HFO blend currently with less than 1,400 GWP. Typically we're air cooled. Each unit is air cooled unless those design conditions dictate something else. And if we need to do something else, it'd most likely be an adiabatic design. Part of, in addition to getting the loads or the capacity, your compressors closer to the loads, we've implemented piping practices like loop piping and things like that have decreased our overall charge of these systems. Next slide, please. So as we're looking to change our architectures and get to something potentially with even lower GWPs, we've kind of put these new architectures, at least in our minds, in the kind of 3 buckets. You got your self-contained, and I should probably call that micro distributed, to kind of keep with the theme here. CO2 and what I'll talk about a little bit more detail, A2L distributed. There may be obviously more options or variations of these, but these are kind of the base three. And depending on your new store design, size, location, any one of these could work. However, as we're looking at our existing store bases, remodeling existing stores poses a lot more, many more challenges. Trying to keep the store operational while changing to these new architectures. We do not see any one of these solutions being suitable for all of our scenarios and all of our locations. We need a combination of technologies, and quite honestly, we see a combination of these technologies potentially in one given store to address all of our needs. And most importantly, I guess the sum of this is we need options. So we need to have the option of different technologies to fill different roles in all of our stores and applications. Next slide. So what would an A2L distributed option look like? Obviously, you could go the more micro distributed routes where you're less than 50 pounds per unit. But we're kind of looking to keep something very similar with what we have today. We're very happy with this kind of distributed, a little bit more macro distributed design. It's very efficient. It's very good on low charge. And obviously it's been very reliable. So if we start looking at the A2L options, obviously you need to use an A2L, probably most likely below 150 GWP. The charge limits due to the A2L being a mildly flammable refrigerant by definition, makes us look at more smaller distributed units. So I'm not saying going to full micro distributed. What I'm saying is we'd go to a smaller, slightly smaller distributed unit. So instead of those 4 to 5 units, we're potentially looking at 10, maybe 12 distributed units around the store. I'm not the expert on the calculating the charge limits with A2Ls, but typically you're in the 160 to 180 pound range. So that's what you would need to keep each one of those systems around to meet the codes. Design considerations such as the location of your equipment, the condenser type, the receiver size, is all extremely important as you're looking at this to reduce that charge even further, to reduce the amount of equipment that you have. And then one of the items that A2L kind of bring to the table that is a little different than what we've done in the past. I know everybody's looking at leak detection, but leak detection is required with A2L, and it's required on a level that most of us don't have in our stores today to not only detect the leaks, but to mitigate the leaks. So that's going to be a little bit new. It's going to be obviously at cost, but it'll also have some benefits we can talk about here in a minute. Next slide. So what are we seeing as potential benefits for A2Ls? Obviously training. This technology, while it is a mildly flammable refrigerant, it is no different than what we're doing today. It operates like the equipment that a lot of us use today, which with HFC or HFO blend refrigerants. Efficiencies, case studies and evaluations show that this kind of design is potentially more energy efficient than other potential architectures out there. So that's obviously something we're very interested in. Components. Similar, if not the same as what we use today. I'll actually have components in the con department as well. I'll talk about that on the next slide, but the components are very familiar. Again, back to that training, we know what the parts and pieces are. Upfront cost potential for lower component and install costs compared to other items, and on that even goes for operating costs with obviously I mentioned the energy efficiency potential, but maintenance costs would be very similar to systems we operate today. So you wouldn't anticipate anything going up there. But then back to the leak detection components of this, these systems will operate with a much lower leak rate than systems we operate today. So because of what we have to put into the cases to detect and mitigate those leaks. Next slide, please. So what are our challenges? Obviously, number one is code adoption. Without significant effort, we really can't build one right now. We need these codes. The codes are written. We need them to be adopted. And that would allow us to actually start moving forward with a little bit more testing. We're working on moving forward right now, but that is a serious hang up with this technology at the time. I say timeline, will these components and codes be in place by the time we need them? We don't know exactly when these GWP restraints will be in effect nationally. We have some state by state regulations that, it'd be nice to have this as an option to meet some of these regulations. But when we're looking at the bigger picture, will the industry be able to pool these components and technologies and refrigerants together for us to actually use them in a retail environment? Again, I mentioned components. It is a bonus that they are very similar to what we do today, but while they're similar, they do need to be rated for A2L. So you can't just take an A2L and put it into a component that is using a refrigerant today. And I'd like to make a point here that just like with CO2 or R290, an A2L cannot just be put into an existing system, right? And just like with CO2 and R290, all components, including your cases and piping, will most likely not work. All of that equipment will have to be changed out when moving to these new refrigerants and new architectures. Leak detection, again, it is a bonus, but there is a cost to that. And there's a cost to it up front. There is a cost to maintain it for you to get the benefit out of it. And then the mitigation piece of leak detection, that another cost. Each case will need isolation valves in the event of a leak, to prevent that leaking refrigerant from any more out of the system. It basically leaks what's in the case. But this will pose new challenges. Not only will we have to maintain it, but the store personnel will have to understand what's going on and how to react to this micro detection of leaks. And that's something the industry really hasn't dealt with yet. But so those are the challenges. I believe that is my last slide, kind of covering what we're seeing with A2Ls and the potential for this little mixed in between size of distributed and micro distributed A2L systems.
Muted. There we go. Thanks so much, Mike. I appreciate you giving us that overview. And on the slides where you were talking about the three various options that you're looking at, CO2, is that CO2 transcritical or a number? What do you mean by that?
Yeah, so I mean, obviously there's multiple technologies of CO2. We personally have experience with transcritical. So as we're looking at those options, that's really the more viable option that we see for our locations. And again, every store is different, right? What works for us might not work for someone else. But in our environment, CO2 transcritical is the most viable version of the CO2 technologies.
Great. No, I appreciate that message and the fact that options are needed.
Thank you.
Great. So now we'll hear from Andrew Beall, and he'll give us perspective on WinCo and experiences on the micro distributed side.
Well, all right. Thank you, Danielle. Hey, let's to start off here. I do some utter, so it isn't boom, all right? So, so on encoded data, we are currently in 10 states, 138 stores now. A typical store is 85,000 square feet. We have 145 cases and walk-in evap coils to total. We currently have nine new MDS stores and 4 remodeled. They all have 448A. So the goals here are to stay under that 50 pound charge, and to meet the 26 and 30 carb targets. Currently with the 4 remodeled stores in California, we hit 39. We're at 39% of that target for 2026 and 18% towards 2030. Next slide. So our technology that we are using is we have 2 fluid coolers, and all the cases and coils. They're all tied to a central condensing loop. The advantage this year are that we are currently we're currently able to utilize the same case manufacturer as we had for the BX. Currently for 48 is easier to get than the CO2 is propane. We utilize a lot of open medium temp type cases. So the charge amounts don't work for us. Next slide. So the number one performance metric here is to meet par. Into terms of energy, we have a store that's been remodeled since early to 20 to 21. It is looking like it is saving us energy. The others, they've only been remodeled since April. So the data isn't there yet. Into terms of maintenance, the oldest store that we currently have is January of 21. So it's still early on. Next slide. Thank you. Technicians. When we had first talked about putting in the yes, we all thought you at the cases, pipe up to burn on, and it works. Well, that isn't accurate. There's been a burning curve. There's been some component failures. So a case is setter, a pipe hitter, a controls a controls installer, and a startup check. They're all needed here. And the startup tech has to be an actual startup tech. They can dig, deep, check the adage. He's challenge the manufacturer, challenge these is fine. That's the kind of that's the kind of startup tech that we need. Him important. All techs, they need to know what and when to ask questions. The rule is, if you have spent an hour and you still don't know, ask. And then the biggest thing is all texts must be willing to earn. I've had techs call me on a Friday at midnight, and that's awesome. You know, call, ask. You know, if I don't have the answer, I will get it. Next slide. So on the hydroponic piping, we utilize polypropylene piping. And it is welded. It acts as a single pipe then. So it is important to it is important that the hydronic piping installer is a mechanical piping installer. They know how to phase. They know how to prefab. They know how to run the pipe level. They understand and hushing, like all, and they understand how to assemble the pipe. So that is it. Danielle.
Thank you, Andrew. So now that we've heard a little bit about distributed and micro-distributed systems and experiences from these two retailers, we'll go to a few questions. So again, as a reminder, if you have a question, you can type it into the Q&A section. First question is for you, Mike. You mentioned that a typical store size is around 120,000 square feet. What would you estimate is the percentage of that square footage that's refrigerated?
Yeah, I've actually been digging around to make sure I had the right thing here. I don't have it as a percentage, but that store typically is about 1,200 MBH.
Okay.
So that's about how much capacity we have or load that we have in that typical 120,000 square foot store.
And do you also look at the percentage energy in terms of like how much of the total building energy does the refrigeration system use on average?
Yeah, it's been a while since we've done a little while since we've done studies on it, but typically our current systems that we use are probably around the 40% of our total energy usage in a store.
Okay. That's a little lower than average, right? I usually think of it as 50 or 60%.
Yeah, typically they say 50, but like I said, we're very happy with the efficiencies of our refrigeration system today.
Great. Another question for you. When you're looking at the cost to convert to an A2L system, the question is asking for the cost to convert, but I think maybe what's more applicable is cost compared to what, right? So I don't know what your baseline might be, but what percentage of a typical maybe maintenance or something would cost to convert? Maybe
yeah,
what is your baseline?
I can kind of answer that two ways. One, I'd say we're looking at it to be very similar, maybe a little bit more expensive than what we do today. We would think that would come down in cost as we get more familiar with components and the components are more readily available. That's where we anticipate being very similar to what we do today. But I would say if we are taking an existing store and you were to convert to something like this, it would be very similar to converting to anything else, CO2 or any other technology. It's a gut job, so it gets very expensive very fast.
Okay, that's helpful. Another question is around choosing between a micro distributed system using propane versus an HFO A2L. Do you anticipate propane to be more energy efficient? And this might be a question for you both.
Yeah, I'll answer that this way. Just comparing to what I was discussing. If you're comparing a micro distributed A2L system versus a propane, yeah, propane probably would be more efficient. But what I was talking about was somewhere between that micro distributed and that macro distributed, right? So for us, if I went micro distributed, we'd have 300 compressors in the store. Where I'm looking at the macro, I might be around 16, 18. With that design. So I think it would be our numbers say it's close to efficiency parity when you compare the two different architectures, but if they're same architecture, I would agree propane is probably more efficient. Might defer that to our refrigerant experts, but with what we're evaluating with the in-between system there, we might actually be a little bit more efficient, and I think we'd certainly have less equipment.
If I could just expand on Michael's point for a minute, I think that really when people talk about efficiency of refrigeration systems, it's important to remember we're talking about two different things: the thermal efficiency of the refrigerant itself, how much refrigeration capacity per pound of refrigerant, and the mechanical efficiency of the refrigeration system. And then there's obviously limitations, but the compressor systems can be designed more or less efficiently, and more or less efficient gases can be used as a refrigerant. So if you could, to Michael's point, leverage a higher charge limit to reduce the overall number of compressors by using A2Ls because you're limited by the construction codes on the use of propane, then definitely that could be designed as an overall more efficient system. But if you're looking at kind of like for like, propane is a more thermally efficient refrigerant than most of the A2Ls, but you can't use it in the same way. So you have to look at the whole system and work with your consultants and the manufacturers and everyone to see what's really going to be best for my store. But as that charge limit gets increased and those codes get adopted, you could design that intermediary system between macro and micro with propane per se, and it'll be even more efficient than the option with the A2L when we get there. So you've got to look at both the refrigerant and the compressor systems.
Thanks, Ben. And kind of what I hear you saying, Michael, too, correct me if I'm wrong, but for the distributed system type you're looking at, there's not an option with propane because even with the higher charge limits, going up to 300 or 500 grams, that wouldn't be enough in this system architecture.
Correct. Yeah. This type of architecture is a larger charge limit, right? Is a much larger charge limit.
And then Andrew, any comments on the trade-off in terms of energy efficiency? You would expect propane to be in the higher charge limits to be more efficient or less efficient than 448?
I would expect it to be more efficient. However, you are going to go from a hundred and 45 answers now to 200 and whatever. the maintenance overall becomes an issue now.
Yep. All right. Probably the last question we'll have time for. There's a question about overall experiences with energy performance, maintenance, and then the part I'm really interested to hear you talk about is complications of control systems associated with a distributed system that needs a water loop condenser. I guess in general, are you seeing increased complications with controls?
Is that to
Yes. Mhm.
Daniel? We are. We run 4 palm hoops, all right? If we have one case that is off, it kills that whole hoop. So we have to check every case then. So yep. Yeah, and boy, and we went from about 1,000 points to about 10,000 now. So yeah.
Yep. A lot more points of failure. Great. Well, then I'll just end it here with what I think, and Mike, correct me if I'm wrong, but one of the key takeaways, is that in looking at both new store construction and existing stores, retailers need many different options to meet regulatory goals as well as, your own corporate sustainability goals. And one way that policymakers can help support you in those goals is by making sure that the building codes are updated to allow the most number of choices possible.
Absolutely. And obviously the one thing to keep in mind is not just that, like I mentioned before, your GWP, but your total greenhouse gas emissions, right? We might have a great refrigerant that has a very low GWP, but it's very expensive to operate, which makes, we're generating more power to run it, right? So, we need to find that mix, that good balance of those refrigerants and efficiencies.
Great. And we'll be talking more about that in our session on Thursday of what you're referring to, reducing charge and also strategies to reduce leak rates. It's also an important part of the overall emissions picture. So thank you so much for sharing this information today. And thank you in the audience for joining us. Have a good rest of your day.
Thank you.